Earth orbits the Sun at 18.6 miles per second. Stable. Predictable. Now, imagine that orbit interrupted. Imagine the Sun replaced by an object with the same mass, but compressed into a sphere smaller than Manhattan. A black hole. This is not science fiction. Black holes are real, and their physics is well defined. Today, we run the simulation, not with speculation, with general relativity, tidal mechanics, and observational data. What actually happens if Earth crosses the event horizon? Black holes are not cosmic vacuum cleaners. They are regions of space-time where gravity is so intense that nothing, not even light, can escape beyond the event horizon. The nearest known black hole to Earth is Gaia BH1, approximately 1,560 light-years away. Sagittarius A, the supermassive black hole at our galaxy's center, is about 26,000 light-years distant and has a mass of 4.6 million suns.
None of these pose a threat.
Earth is not on a collision course, but the question is useful. It forces us to test our understanding of gravity, time, and matter under extreme conditions. This scenario is a stress test for physics, and the answer reveals how fragile and how resilient our planet really is. First, a critical point. If the Sun were instantly replaced by a black hole of the same mass, Earth's orbit would not change. Gravity depends on mass and distance, not on whether that mass is a star or a singularity. We would not be sucked in. However, this scenario assumes Earth is already on a trajectory toward a black hole. As we approach, two effects dominate: gravitational gradient and tidal forces. At a distance of several 100,000 miles, the side of Earth facing the black hole experiences stronger gravity than the far side. This difference is a tidal force. The Moon creates tides on Earth's oceans. A black hole creates tides on Earth's solid crust. The math is the same, the magnitude is not. The tidal acceleration across Earth's diameter is given by the formula delta A is approximately 2gm by R3 times delta R, where m is the black hole mass, r is distance to the black hole, and delta R is Earth's diameter, about 7,918 miles. For a stellar mass black hole, 10 solar masses, this force becomes destructive at roughly 620,000 miles. For a supermassive black hole like Sagittarius A star, the event horizon is larger and tidal forces at the horizon are weaker. Earth could cross the event horizon of a supermassive black hole largely intact at first. But for a stellar mass black hole, tidal forces would tear Earth apart before we reach the event horizon. This process is called spaghettification.
Rock, metal, atmosphere, everything is stretched into a filament. Friction heats the material to millions of degrees. It emits X-rays. To a distant observer, Earth would appear to brighten, then fade, as matter crosses the event horizon.
General relativity predicts time dilation. As Earth approaches the event horizon, time on Earth runs slower relative to a distant observer. At the horizon, time appears to stop from the outside. From Earth's perspective, the fall continues. We cross the horizon in finite, proper time. From outside, we never see the crossing. The image of Earth redshifts, dims, and freezes at the horizon. This is not an illusion. It is a consequence of space-time geometry.
The last photons emitted by Earth before crossing
Are stretched to undetectable wavelengths. Information about Earth's final state is lost to external observers. This is the black hole information paradox, an active area of research in theoretical physics.
inside the event horizon.
All paths lead to the singularity. For a non-rotating black hole, this is a point of infinite density. For a rotating Kerr black hole, it is a ring singularity. Our equations break down here. General relativity and quantum mechanics give conflicting predictions.
We cannot describe
What happens at the singularity? We can only state the limits of current knowledge. Earth's matter would be compressed beyond nuclear density. Whether information is preserved, destroyed, or encoded on the horizon remains an open question.
summary.
Earth would not be sucked in by a distant black hole. On a collision course, tidal forces would disrupt the planet before or at the event horizon, depending on the black hole's mass. Time dilation would make the final moments appear frozen to outside observers. The singularity represents a boundary of known physics.
This scenario is hypothetical.
The probability of Earth encountering a black hole is negligible on human timescales, but the exercise is valuable. It tests general relativity. It clarifies the difference between stellar and supermassive black holes. It highlights where our physics ends and speculation begins.
Question for the comments.
If you could design an experiment to test what happens inside an event horizon, what would you measure? Keep it within known physics. Let's discuss.
If you want more analysis grounded in data,
Not drama, subscribe. We cover space science without the hype. Sources for this script: NASA, ESA, and peer-reviewed literature on black hole tidal dynamics and general relativity. Thanks for watching.